Hello everyone, my name is Yushen Luo, and I'm from the Southeast University in China. I'm going to present to you our work, Force-Regulated Elastic Linear Objects Tracking for Virtual and Augmented Reality. Elastic linear objects, such as ropes, cables, and pipes, can be easily seen in our daily life. Although humans are sensitive to shape changes of these objects, it is not intuitive to estimate the external forces which generate the deformation. To facilitate the interaction with elastic linear objects, we propose a method to track their shape deformation and sense the applied forces at the same time. The problem we focused can be divided into shape sensing and force sensing. Embedded sensors are commonly used to directly track the object's shape deformation. However, these sensor-based methods are commonly associated with high costs and difficult installation. In recent years, vision-based tracking methods have also been adopted. These methods are easier to deploy, but need to deal with issues like noises or occlusion. As for force sensing part, many studies model the elastic rod as a nonlinear system and obtain applied external forces through inversely solving it. Other studies leverage curvature of the rod's centerline to deduce the tip loads with a faster computational performance. However, these methods are often prone to noise. Generally speaking, it is still challenging to quickly and robustly track the external forces on elastic rods directly from raw visual information. In this work, we try to tackle this task. Here's an overview of our work. We first capture point clouds from the real thing using a depth camera. Through the proposed methods, we then take the noisy point cloud as an observation to reconstruct its configuration both geometrically and physically. Finally, we render the reconstructed shape and force associated with the rod and synthesize them with the real thing to produce an augmented visualization of the interaction with the object. We use a particle filter framework in tracking process. To reduce the dimension of the search space, we encoded the deformed rod states by forces and torques applied on it. The final state of the elastic rod can be derived through the coset rod model, which describes both positions and orientations of elements along the rod centerline. We then discretize the centerline into a set of transform matrices as the shaped representation of a deformed rod for following computations. Here's a pipeline of our tracking method. In each iteration, we start from the last step state. We first predict the particle's next state based on previous states. Then we randomly sample near the prediction in state space and use the forward simulation model to predict the corresponding shapes in the observation space. Next, we evaluated the likelihood of each shape according to the observed point cloud and calculate the weighted mean of the particles as a final estimation of this time step. In addition, we employ the residual resampling method to evaluate the degeneracy problem, which is often encountered in particle filtering. We designed the likelihood function to compute each particle's weight in estimation. The function consists of two terms. The first term evaluates the similarity between the simulated shape and the observed point cloud. We use the closest point to compute the shape differences, which is commonly seen in ICP-based shape registration methods. In our work, we often attach a fiducial marker at one end to help locate the road. We know that if the node is farther from the marker, the uncertainty range of its position will correspondingly increases. In other words, the more distal nodes are more sensitive to the state change. Therefore, we allocate higher weights to them using the distance in the parametric domain. We also added a physical regularization term which promotes the estimation results to align more closely with certain prior knowledge. For example, if the rod is made of high stiffness material, it will not be sensitive to the force applied at the tangential direction, and we could constrain components in its direction to avoid potential convergence problems. Besides, if we know the rod has a free distal end, we can also penalize the force and torque applied at the end. We tested our method both in simulation and in real world. Our simulation data was generated through SOFA, which is an open source framework widely used for elastic linear objects modeling and simulation. We generated an elastic world in the environment and applied different forces to induce the deformation. The point cloud is generated by randomly sampling positions of the nodes, and we add Gaussian noises to simulate the measurement errors. We tested our method under a variety of cases, including one force at the end, different number of forces at different locations of the road. The road is precurved and road with higher density. The results show that our method is flexible in dealing with different elastic linear objects. We also tested our method under different disturbances, including Gaussian noises, white noises, and occlusions. The results demonstrated our method's robustness to this influence to a certain extent. We compared our method with the previous work. They trained an autoencoder network to reconstruct the road shape from a latent vector, and then employed a particle filter to search the latent control. We generated a continuous sequence of the elastic road's motion and used both methods to track the sample points. We found our method outperformed the previous methods. The learning-based method attempted to fit the nonlinear deformation space into four-layer MLP, while the physics model naturally encoded the deformation using the external forces as the intrinsic control variables, which had a better performance in representing the deformation. We also evaluated our method for the force estimation capability. The estimation on tip force gave an average relative error of 3%, which reaches the level of previous works from 2.2% to 11.4% of applied magnitude. In addition, we verified the effectiveness of our regularization terms through ablation study, as shown in the figure right. We built several interactive applications in both VR and AR. As shown on the left, we developed a tangible user interface to passively track the caster as the input device to a VR system. In this demo, users could manipulate the caster to flexibly produce freeform curves mapped to the VR scene, while in traditional GUIs, they have to specify the control points to model the smooth curves with cumbersome clicking and dragging operations. In comparison, the tangible interaction is intuitive to adjust the shape of the virtual caster. Our method is also beneficial for building augmented reality with elastic linear objects. As shown in the right, we first press an elastic rod to bend back and forth, with the depth camera capturing the interaction and a screen to render the tracked shape and force in real time. The user could intuitively observe the estimated pressing force to help assess the haptic experience in manipulation. We then tested our method with real-world caster whose rest shape is a bend curve. By tracking and visualizing force with our method, we could better estimate the contact status of the caster in the AR view. In summary for this work, we proposed a force-regulated model for tracking the shape of elastic linear objects as well as the external forces exerted on the objects. We demonstrated that the underlying external force configuration is an efficient way to encode the intrinsic state of elastic linear objects. By equipping the particle filter film with the physical model, we show the potential in tracking of elastic linear objects for virtual and augmented reality. We will further explore the power of VR and AR with the estimated geometric and physical information. That's all for our work. Thank you for your listening.